Let's start our review of Lab 1 here with the data report page. That's page 13 in the handout. So you were supposed to ask a question or make an observation, whatever that was for you. Let me just give you an example. You, for example, could make the observation that after you eat a heavy meal, you feel really tired every time. And so that's a good observation. Or you could make the observation that your heart rate increases when you exercise. So it doesn't really matter. Or you could make the observation that the sky is blue. Whatever it is, it's all good. And you should have written something down. So the only thing, when you're making a hypothesis, the only thing you need to pay attention to is the characteristic of a good hypothesis is there's only one thing, and that is it has to be testable. If you can't put it into numbers or do some sort of experiment on it, then it's not a good hypothesis. So coming back to the observation that I feel tired after a heavy meal, I could make a hypothesis that, for example, my body is busy digesting, and so therefore it's taking away attention from other things, and so it just wants to rest and digest, and it's starting the parasympathetic side of your autonomic nervous system, and that's a pretty sophisticated hypothesis already there, but it is testable and therefore a good hypothesis. Now, anytime you are having a hypothesis that's not testable because it's leaving the physical world, so you're going to the spiritual world or superstitial world, and you're assuming that there is something in the food, something superstitious that makes you tired, then you can't test that. So a good hypothesis has to be testable. So that's the point here. Let's take a look at these observations or questions and write a hypothesis. So my car doesn't start. Well, that's a very disappointing observation, but it does happen. So you could make the hypothesis that there's no gas in the tank, or that the starter is broken, or that maybe your battery is dead. All of that would be testable. What's not testable if you say that some evil spirit is preventing your car from starting. So that would be not testable. Let's take a look at number 2. What causes a cold? Good question. So there you could, if you know something about viruses, you could say, well, it's probably a cold virus. It's some sort of infectious particle because it is transmissible. So that kind of stuff. So all of that would be testable. Number 3, why are students sometimes late to class? So nowadays, now that everything's online, hey, we don't even have to worry about this anymore. So you just turn on your computer whenever you feel like it. And but in the old days, before COVID-19, we were wondering why students or instructors are sometimes late to class. And so there are also numerous hypotheses you can form, such as there's no parking available in the parking lot, or your alarm didn't go off, or there was too much traffic, or there was an accident, or whatever it is. So there's numerous hypotheses that would all be testable. What's not testable, again, would be something superstitious that, it was Friday the 13th, and so therefore your alarm clock didn't come off, and that's why. So number 4, what causes insomnia? Insomnia means that you can't fall asleep. So their good hypotheses would be that you had maybe too much caffeine in the afternoon, or that you were really worried about something, or that you were anxious about something, and that could cause you to not fall asleep, or stressed out about something. Not testable, on the other hand, would be saying that there's a ghost in the room, or there's some other superstitious stuff. So make sure that it always has to be testable when you're forming a hypothesis. How about number 5? My computer will not boot up. Well, good hypothesis would be it's not plugged in, or the battery is dead, or the computer has a virus or something like that. So these are all testable hypotheses. So now moving on here to the next page, you're supposed to state whether something is testable by hypothesis or not. And so now the car doesn't start because it's out of gas. Obviously we can test that. All you have to do is put some gas in the tank and see if the car will start then. How about number 2? Adele is a better singer than Madonna. Well, as stated, this is not really testable because you don't have any criteria to what makes somebody a better singer. Now, if you were to say that somebody's a better singer if they can hit a certain note for a certain amount of time and one can do it and the other one cannot, then you could say, yeah, one's a better singer than the other. But as stated, this is not testable by hypothesis. Number 3, my grandmother got cancer because it was God's will that she go at that time. That you cannot test. It's outside of the physical, measurable world. Number 4, exposure of skin to sunlight increases the chance of developing skin cancer. Definitely testable. All you have to do is, and some large scale studies have been done, looking at sun exposure and correlate that with the number of skin cancers that people develop, and there's definitely a link. How about number 5? John Wilkes Booth shot Lincoln because he was possessed by demons. That's what a lot of people believe, but demon possession is not something that we can measure in science, and so therefore this is not testable. Number 6, the dinosaurs were wiped out by the impact of a large asteroid on the Yucatan coast of Mexico. That's what's in all biology books, pretty much. And even though this was an event in the past, you can still run simulations and therefore collect data and so therefore run experiments. So this is actually a testable hypothesis. Okay, so let's skip down here. You're supposed to choose one hypothesis and design a controlled experiment to test the hypothesis. Let's take number 3 and modify it and make it a little bit more up to date. A new vaccine can protect people from infection by COVID-19. Or SARS-CoV-2, the official name of this virus. So, how would you design a controlled experiment? And the NIH people and the CDC people, they are doing those experiments right now. So they are developing a vaccine, and then they need to have a control group and a experimental group, and so then it has to be a pretty large number of people. But so you would use the new vaccine that you think is going to work, and give these people a shot, and then see if you have a lower infection rate in your vaccine group versus the non-vaccinated group, and so see whether there was an effect that the vaccine actually protected people from infection. And those are currently underway, and hopefully we will have a vaccine pretty soon, but it's talking about next year, so probably early next year. But anyway, so that would be a good controlled experiment to do. So let's take a look at the result of the experiment if the hypothesis were true. So if it is true that I think my vaccine is good, then the result of the experiment would be that I have a lower infection rate with coronavirus in my vaccinated group as opposed to the control group. And if the hypothesis was false and my vaccine is worthless, then there would be no difference in the infection rate between the two groups. So here some sort of an introduction to what we will be doing in the next lab, taking a look at statistical analysis, because as soon as you have two groups, you need to analyze. First, you need to form the averages and then compare the two groups. And we talked earlier about the sample size. The larger the better. you have to have at least about 10 members in each group. And if you're enlarging clinical trials, you need to have much bigger groups than that. But sample size really matters. And to have a better, to come to better conclusions, the larger the sample size in general, the better. A statistical significance, there are rules to the game, and we're going to talk in more detail in the next lab about it. The accepted cutoff p-value is for science experiments. If you want to publish this, it's always p equal 0.05. And so then that would consider the event is non-random. So in statistical analysis, you need to have a cutoff value by which you then measure whether or not there is a significant difference between control group and experimental group. And again, we will be talking about that more in the next lab. We already talked about the placebo and double-blind experiment, these two terms. Placebo is a lookalike. Let's say you have your control group, they also get a shot. So at least they think they might have gotten the actual shot. But let's say you just put saline solution into the shot. And the other group, the experimental group, they get the actual coronavirus vaccination shot. So a placebo is a lookalike that makes you feel like that, yeah, you got something. Or when it comes to medication, same thing. Double-blind experiment means that neither the people that are participating in the study nor the people that are administering, let's say in this case the vaccine or some medication, neither one of them knows who is assigned to which group. So they don't know whether somebody's getting a placebo or whether they are getting the actual medication. Some administrator in some office would assign it. So it makes it just it just really makes it for better results, because people tend to wanting to guess, am I in the experimental group or in the control group? And that could affect how they feel about something. The next term here, the burden of proof, is kind of silly, but burden of proof means that you have to show evidence that the claim that you're making is for real, and that means that you have to support that with data or with evidence. And so here, the silly example, evidence for the existence of Santa Claus. Well, you could, I don't know, you ask little kids, they always know what the evidence is for Santa Claus. So it could be, who knows, that milk and cookies are gone or something like that, or the presents are there. And possible evidence against the existence of Santa Claus would be that, hey, it was Dad who was in a shopping mall with a suit and a beard, or it was the presents were put under the tree by your parents or something like that. So anyway, I think you get the idea. Here are some definitions that also will come again in the next lab. A positive statement versus negative statement. So the terms that I like better are the null hypothesis. Null hypothesis means there's no change. There's no difference. The medication had no effect. The shot had no effect. The vaccine didn't have effect. Null hypothesis means there's no change. No difference between the experimental group and the control group. The alternative hypothesis is that there was an effect, or the positive statement here. So the alternative hypothesis means that the vaccination was good, that it did help, that the medication did make a difference. So there was a difference, a significant difference between the two groups. And the burden of proof is always on the one to make the claim. Now let's skip down here to part C, and I'm going to put all of the metrics problems into a separate recording, but part C is fairly quick. So the field diameter, if you would have done some microscopy, you would have been able to measure the field diameter using just a millimeter ruler, and at low power or 40x total magnification, you should have seen 5 millimeters of field diameter. At medium power, 100x total magnification, you should have seen 2 millimeters of field diameter. And at high power, 400x, you can't even see a full millimeter anymore. It's 0.5 millimeters. The pointed diameter doesn't really matter because that thing doesn't change as you go up in magnification. But let's take a look at part 2 here, determining cell size. So here on number 1, let's assume that we are looking at cheek cells, and let's say we can see across our field of view under the microscope that there's approximately 8 cells that we could line up across the field of view. So if we wanted to know approximately how big each cell is, then we would say, okay, so I'm at 100x total magnification. That means I have a field diameter of 2 millimeters based from up here. That's 2000 micrometers. So 2000 divided by 8, and that's equal to 250 micrometers. So that means our approximation of the size of cheek cells is 250 micrometers. Here on the bottom on 2, let's say you were to look at a hair at 400x total magnification. That means our field diameter is 500 micrometers, and let's say we could fit about 5 hair across the field diameter. That will be 500 divided by 5, so it's 100 micrometers total size.